What if I told you the universe holds forces so extreme, so unimaginably powerful, they could wipe out a planet in the blink of an eye, or forge new worlds from pure chaos? Somewhere out there, hidden among galaxies and stretching across billions of light years, are energies that dwarf every bomb, every sun, every black hole we've ever imagined. Forces that twist space, fracture time, and challenge the very limits of physics. They're not science fiction. They're real, and they might already be shaping the future of everything we know. So, what is the most powerful thing in the universe? Is it a supernova exploding with the fury of a billion stars? A black hole devouring matter and bending time like a rubber band? A mysterious beam of radiation that can pierce through planets like they're made of glass? Power, it turns out, comes in many forms, and not all of them scream as they pass. Some whisper, some blaze, some pass silently through your body every second without you even knowing. In this journey, we're not just going to talk about explosions or gravity. We're diving deep into the most intense phenomena that nature has to offer. The things that break atoms, crush stars, and stretch the imagination. We'll explore subatomic bullets that hit Earth with more force than anything humans have ever built. Ancient rocks from space that once ended life on our planet and could again. Wandering planets with no suns that drift like cosmic wrecking balls. Stars that collapse, explode, or even destroy themselves from the inside out. Black holes feeding at such a rate that they unleash jets brighter than entire galaxies. The quiet power of dead stars spinning faster than a blender blade. And the terrifying idea that the entire universe might not be as stable as we think. We'll also go beyond the observable, into the realm of theory, where space-time might tear, reality might reboot, and computation itself could trigger an energy release unlike anything we've seen before. Are you ready to travel to the very edge of physics and imagination? Let's begin. The brightest explosions the universe has ever seen. Imagine a flash of light so powerful it outshines everything else in the universe for a few brief seconds. So intense, it could strip a planet of its atmosphere from across a galaxy. So distant, yet so bright, that we can still detect it billions of years after it happened. These are gamma-ray bursts, or GRBs, and they are the most luminous electromagnetic events we know of. First discovered in the 1960s by US satellites looking for nuclear explosions on Earth, these bursts of gamma rays, the most energetic form of light, were found to be coming not from Earth, but from deep space. And they were unlike anything else. Each burst lasts only seconds, sometimes just milliseconds. But in that time, a single GRB can release as much energy as the Sun will emit in 10 billion years. Yes, billions of years of sunshine in a single blast. So, what causes these titanic flashes? There are two main types of GRBs. Long-duration GRBs, lasting more than 2 seconds, sometimes up to several minutes. These are thought to be the deaths of massive stars. When a star much larger than the Sun runs out of fuel, its core collapses into a black hole. As the surrounding material falls in, it forms a spinning accretion disk. Under the right conditions, this disk launches narrow jets of plasma, at nearly the speed of light. If one of those jets is aimed at Earth, we see a long GRB, a burst of gamma rays that can be detected from billions of light-years away. After the burst, the surrounding gas continues to glow in X-rays, ultraviolet, and visible light. This is called the afterglow, and it helps astronomers trace the burst's location and study its environment. Long GRBs are often found in star-forming galaxies, where massive stars live and die quickly. They may be one of the primary ways the universe recycles elements from dying stars into the interstellar medium. Short-duration GRBs, lasting less than 2 seconds, often just a tenth of a second. These are believed to come from neutron star mergers, the same collisions that cause kilonovae. When two neutron stars spiral into each other and merge, they may collapse into a black hole and release a brief but intense jet of gamma rays. Unlike long GRBs, these short bursts tend to occur in older galaxies, where binary neutron stars have had time to form and merge. Some short GRBs may also result from neutron star black hole mergers, another exotic form of cosmic violence. A third possibility, ultra-long GRBs. There's growing evidence that some GRBs may last thousands of seconds, potentially linked to blue supergiant stars or magnetars undergoing unusual collapses. These are still under investigation and may represent an entirely new class of stellar death. But regardless of the cause, GRBs are dangerous. If a GRB occurred within a few thousand light-years of Earth and its beam hit us directly, it could wipe out the ozone layer, triggering mass extinctions. Some scientists have even speculated that past extinction events on Earth may have been linked to distant GRBs. Thankfully, they're rare, and space is big. But the sheer power of a GRB focused into a narrow beam means even a distant one can have a measurable impact. In recent years, satellites like NASA's SWIFT and Fermi have detected hundreds of GRBs, helping us catalog and study them in greater detail. Some have been traced back to the edges of the observable universe, giving us insights into the first generations of stars. One of the brightest ever observed, GRB 22109A, was so powerful it was dubbed the BOAT, brightest of all time. It was detected in 2022 and is still being studied for the many anomalies and mysteries it revealed. GRBs challenge the limits of physics. They teach us about black hole formation, jet dynamics, nuclear reactions, and relativistic physics. And they remind us that in the vast dark of space, there are still moments of blinding, violent brilliance, moments where the universe screams. Where crushed stars collide, and the universe makes gold. Somewhere out in the vast silence of space, two dead stars circle each other for eons. Invisible, relentless. Their dance grows tighter, faster, more desperate, until the final moment. And then, impact. The result isn't a supernova. It's something rarer, stranger. A burst of light and gravitational waves so powerful, it shakes the very fabric of space itself. This is a kilonova, one of the most violent and precious events in the universe. It begins with a binary pair of neutron stars, orbiting each other for millions or even billions of years. Over time, their energy bleeds away, not through heat or radiation, but through gravitational waves. Ripples in the fabric of space-time predicted by Einstein and confirmed just recently. As the orbits decay, the stars spiral inward, and then they collide. The impact is unlike anything else. Two ultra-dense objects, each the size of a city, each heavier than the sun, slamming into each other at a significant fraction of the speed of light. The collision shreds the stars apart, launching debris in every direction. But this debris is special. It's not ordinary gas. It's neutron-rich matter, perfect conditions for something truly magical. Inside this cloud, a process unfolds known as rapid neutron capture, or the R process. Atoms smash together, capturing neutrons so quickly that they build up heavy, complex nuclei in seconds. In that brief moment, the universe manufactures gold, platinum, uranium, and other elements too heavy to form in typical stars. Yes, your wedding ring, your smartphone contacts, the rare earths in your electronics. They all may have originated in a kilonova billions of years ago. Without these collisions, the universe would be poor in heavy elements. We would be poorer too, literally and cosmically. The light from a kilonova looks different from a supernova. It rises quickly, within a day or two, and fades within a week. It glows oddly, shifting from blue to red as the heavy elements form and cool. It doesn't just shine, it transforms. For years, kilonovae were theoretical. Then came 2017. Two neutron stars merged in a galaxy 130 million light-years away. And for the first time, we detected both the gravitational waves and the visible light from the same event, GW 170817. It was a turning point. Telescopes around the world scrambled to catch the light. And in that dim flicker from a distant galaxy, we saw the signature of a kilonova, the first real glimpse of gold being born. Estimates suggest that a single kilonova can produce enough gold to fill Earth's oceans many times over. What happens next depends on mass. Sometimes the merged neutron stars collapse instantly into a black hole. Other times, they form a supermassive neutron star, briefly stable, spinning rapidly, with magnetic fields so strong they hurl out jets of matter at near-light speed. These jets are thought to power short gamma-ray bursts, flashes of energy lasting just a couple of seconds, but releasing more energy than our Sun will produce in its entire lifetime. Today, observatories like LIGO and Virgo listen for the faint tremble of gravitational waves. When one's detected, telescopes pivot instantly, trying to catch that fleeting glow before it vanishes. Every new kilonova observed tells us more about how matter behaves under pressure, how elements are forged, and how extreme physics shapes the cosmos. And here's a thought to carry with you. The gold you wear, the platinum in your circuits, the rare isotopes in your bones, some of it was made in the death spiral of two crushed stars. Stars that lived, died, collided, and in that final embrace, left behind pieces of themselves that we now carry. When a single rock rewrites the story of Earth. Unlike the ghostly, invisible cosmic rays that strike without a trace, mega-asteroids make their presence known with catastrophic finality. Picture a mountain of metal and stone, 10 kilometers wide, hurtling through space at tens of thousands of kilometers per hour. Now imagine that it slams into Earth. What happens next isn't just an explosion, it's an extinction event. The energy released by such an impact would dwarf every nuclear weapon on the planet combined, not once, but many times over. A force so immense It rewrites ecosystems, ends entire eras, and scars the planet for millions of years. Here's the physics. Any object moving at high speed carries kinetic energy. When a massive asteroid crashes into Earth, that energy has nowhere to go but outward. Instantly, the crust shatters. The impact zone turns to plasma. The ground shakes violently. A crater forms deeper than anything humans have ever excavated. Within seconds, the air ignites. Shock waves race across continents. Winds roar faster than hurricanes, driven not by weather, but by raw impact energy. Wildfires ignite thousands of kilometers from the blast zone. Animals, forests, entire ecosystems vanish in moments. If the impact occurs in an ocean, and considering Earth is mostly water, that's likely, tsunamis hundreds of meters tall would radiate out from the site. These waves are nothing like the ones we know. They're not rolling breakers. They're walls of water moving faster than jets, capable of smashing into coasts on the opposite side of the planet hours later. And then comes the sky. The impact vaporizes rock and sends trillions of tons of dust and soot into the atmosphere. As this debris rains back down, it superheats the atmosphere, turning the sky into a furnace. Eventually, a global layer of particles settles into the upper atmosphere, blocking sunlight. Temperatures plunge. Photosynthesis stops. Crops fail. An artificial winter begins, a world without warmth, without food, without time to adapt. We've seen this happen before. Roughly 66 million years ago, an asteroid about 10 kilometers wide slammed into what is now the Yucatan Peninsula in Mexico. The Chicxulub impact is etched into Earth's geologic record, a buried crater 180 kilometers wide. That one rock wiped out 75% of all species on Earth, including the dinosaurs. It didn't take centuries. It took years. Some life survived. The small, the lucky, the adaptable. But the world was forever changed. This wasn't the first asteroid impact Earth has suffered, and it won't be the last. Craters on every continent are silent testimonies to past collisions. Some were massive, others modest. Some left only microscopic traces buried beneath sediment. But all of them were reminders that space doesn't care about our schedules. Today, we scan the skies for these cosmic intruders. Telescopes and tracking networks like NASA's Near-Earth Object Observations program catalog thousands of asteroids. But not all are found in time. Some pass close before they're even seen. A few have entered Earth's atmosphere without warning, like the Chelyabinsk event in 2013, which shattered windows and injured over 1,000 people. A future impact is not a question of if, but when. Some scientists are racing to build planetary defense systems, spacecraft that could nudge asteroids off course with kinetic impactors, nuclear devices, or solar sails. But these technologies are untested in real-world emergencies. A 10-kilometer rock wouldn't need to explode. It would just need to land. And yet, despite the danger, there's something awe-inspiring about these cosmic hammers. They are agents of change. They churn the crust, mix the elements. They may have even delivered water and organic molecules to early Earth. Ingredients essential for life: destruction, creation, renewal. Mega-asteroid impacts are nature's way of resetting the stage. The question is, will we be watching when the next curtain falls? When stars are too strong to survive themselves. Most stars die because they run out of fuel. Their cores can no longer support the weight above them. Gravity takes over, and they collapse inward, sometimes quietly, sometimes in spectacular fashion. But a rare few stars meet a very different fate. They don't die because they're weak. They die because they're too powerful to live. These are the pair instability supernovae, among the rarest and most violent stellar deaths in the universe. And unlike anything else, they tear themselves apart from the inside out. To understand them, we have to go deep into the hearts of the most massive stars in the cosmos, those weighing between 130 and 250 times the mass of the Sun. Their lifespans are short, just a few million years, and they burn hot, bright, and fast. At their core, nuclear fusion rages. Hydrogen becomes helium, then carbon, then oxygen, then heavier elements. Each fusion reaction generates energy, which pushes outward and balances the immense gravitational weight of the star. But in these behemoths, something strange happens as the core heats up to over 1 billion degrees. At that temperature, photons, particles of light, begin to behave differently. Instead of simply exerting radiation pressure to keep the star stable, some of them transform into matter. Specifically, electron-positron pairs, particles of matter and antimatter. When this happens, radiation pressure drops. Gravity, which had been barely held in check, now gains the upper hand. The star begins to collapse, but it doesn't end there. That collapse rapidly heats the core, triggering a runaway fusion reaction. Oxygen, neon, and other heavy elements ignite all at once, releasing an unimaginable flood of energy. The star doesn't collapse into a black hole. It doesn't even form a neutron star. It just explodes completely. No core survives, no remnant remains. It's total annihilation, a cosmic self-destruction. The explosion hurls vast amounts of material into space at thousands of kilometers per second. And with it, a treasure trove of elements: oxygen, carbon, silicon, even iron, enough to seed galaxies with the building blocks of life. We think these supernovae were more common in the early universe, when the first generation of stars, so-called population 3 stars, formed from pristine hydrogen and helium. Without heavier elements to cool the gas, those stars could grow enormous. And some likely ended their lives in this very way. Modern telescopes like the James Webb Space Telescope are now peering back across billions of light years, searching for the fingerprints of these ancient explosions, flashes that may have helped shape the structure of the early cosmos. And we may already have seen them. Supernova SN 2007 by, for example, shone brighter and longer than a typical explosion. Its light carried unusual amounts of nickel-56, consistent with predictions of a pair instability supernova. It may have been the first we ever observed in real time. Another, SN 2213-1745, burned even brighter and longer. Though still under study, it may be an even more extreme example. A window into the rarest kind of stellar death. These events aren't just visually stunning. They're vital to cosmic chemical evolution. In low metallicity dwarf galaxies, where the gas hasn't been polluted by many generations of stars, pair instability explosions could be responsible for strange elemental patterns we can't explain any other way. They also challenge our models of stellar physics. The feedback loop that destroys these stars, light becoming matter, reducing pressure, triggering collapse, triggering runaway fusion, feels almost like a paradox. Too much energy becomes the very cause of destruction. But it's real, and it's terrifyingly beautiful. If the star is just a bit smaller, it might survive. Barely. If it's even more massive, it might collapse straight into a black hole, skipping the explosion altogether. But in that narrow range, it dies in a blaze so thorough, so intense, that the universe gets reshaped in its wake. These aren't just explosions. They're declarations, from stars too massive to be stable, too hot to cool, and too proud to die quietly. The quietest explosions you've never heard of. When most people think of a supernova, they imagine something dramatic. A titanic star collapsing under its own weight, triggering a blast that lights up an entire galaxy. That's the textbook version. And it's real. But not all stars die with a bang that shouts. Some stars die with a whisper, and their quiet destruction hides secrets that might reshape our understanding of how stars live and die. These are electron capture supernovae. Rare, subtle, easily mistaken for something else. And for decades, even astronomers didn't know they existed. Let's rewind. Stars between 8 and 10 times the mass of our Sun sit in a strange middle ground. They're not massive enough to go out in a typical iron core collapse supernova. But they're too heavy to fade into white dwarfs like smaller stars do. They walk a cosmic tightrope. And eventually, something has to give. Inside these stars, fusion builds up heavier elements, not iron, but a mix of oxygen, neon, and magnesium. Over time, their cores become densely packed. Atoms are squeezed closer together. Electrons, normally zipping around carrying energy, start to vanish. Under immense pressure, electrons are drawn into atomic nuclei, where they combine with protons to form neutrons. It's a quantum process called electron capture. And as more electrons vanish, something terrifying happens. The pressure that held the star up begins to fade. Electrons act like tiny supports, resisting gravity. Take them away, and gravity wins. Collapse is sudden, violent. The core falls in on itself. The outer layers follow, plunging inward at thousands of kilometers per second. When the infalling matter slams into the newly formed neutron core, it rebounds, sending out a shock wave that tears the star apart. Compared to typical supernova, electron capture explosions are dimmer, slower, and harder to detect. But don't be fooled. They are just as important and possibly far more common than we realize. They may hold clues to how neutron stars form, clues to the chemical signatures we see in ancient stars, even clues to how the early universe seeded the elements we now find in planets and in us. Electron capture supernovae produce specific isotopes, rare ones like calcium-48 and nickel-58, that aren't found in the same quantities in regular supernovae. Their light fades differently. Their spectral fingerprints carry unexpected traces of neon and magnesium. And thanks to new telescopes and advanced modeling, we're finally starting to tell them apart from their louder, flashier cousins. Some may even help trigger new stars. The shock waves from electron capture supernovae can ripple through nearby gas clouds, compressing them, lighting the spark for the next generation of stars. In this way, even a quiet death becomes a catalyst for new beginnings. But the path to this kind of death is narrow, too massive, and the star becomes a traditional iron core supernova. Too light, and it cools into a white dwarf. Only stars in a very specific mass range, with the right balance of oxygen, neon, and magnesium, and just the right rate of mass accumulation. only they walk the path to an electron capture supernova. The neutron stars left behind are also different. They may spin more slowly, have weaker magnetic fields, or different core structures entirely. Some of the faint, cold neutron stars we've observed might be the remnants of these quieter cataclysms, the ghosts of stars that didn't scream when they died. It's a cosmic irony. These supernovae don't dominate the sky. They don't dazzle the telescopes, but they fill in the blanks, the mysteries in our stellar family tree, the strange chemical ratios, the silent neutron stars. They are whispers in the cosmic archive, speaking volumes to those who know how to listen. A second explosion, after death. We used to think that neutron stars were the end of the road, that once a star collapsed into a sphere of neutrons, the story was over. But what if it wasn't? What if, deep inside these ultra-dense remnants, something even stranger happens, something that triggers a second explosion, more powerful and more mysterious than the first? Welcome to the idea of the Quark Nova. It's still a theory. We haven't seen one, but the physics is tantalizing. Here's the setup. After a massive star explodes in a traditional supernova, its core collapses into a neutron star. Dense, hot, balanced, barely, by the quantum pressure of tightly packed neutrons. But that pressure has limits. And if the neutron star gains more mass, perhaps from a binary companion or from leftover fallback material, its core might reach a breaking point. Under even greater pressure, the neutrons themselves could break down. Not into protons and electrons, but into their most fundamental components, quarks, the building blocks of all matter. Suddenly, the core transforms into something exotic. Quark matter, a dense, strange soup of up quarks, down quarks, and possibly even strange quarks. This transition wouldn't be peaceful. It would be violent. The structure of the star would collapse inward even further, then rebound outward in a massive shock wave. This is the Quark Nova, a second explosion following the original supernova, possibly hours, days, or even weeks later. And it might explain some of the weirdest things we've seen in space. Some distant supernova don't behave like they should. Their brightness doesn't just rise and fall, it spikes again, as if there's a second blast hidden beneath the first. Others have strange chemical signatures that don't match the elements made in normal explosions. A quark nova could be the missing piece. The first explosion sends material outward. Then, the second, quark-powered blast catches up, slams into the debris, and unleashes a new round of energy. The result? Hyperluminous supernovae, among the brightest events in the known universe. And it's not just light. A quark nova might also release jets of high-energy particles, possibly even gamma rays. Some scientists think it could help explain certain kinds of gamma-ray bursts that don't fit the standard models. And then there's the matter of strange matter. Quark matter, especially if it contains strange quarks, might be more stable than ordinary matter. If that's true, then once a tiny bit of strange matter forms, it could start converting everything it touches into more strange matter, like a chain reaction. A neutron star could be consumed from within, transforming entirely into a quark star, an object even more exotic, dense, and mysterious than anything we've seen. No one has ever confirmed the existence of a quark star, but they may be out there, quiet, cold, compact remnants of this second explosion. They might spin differently, glow differently, emit strange signals, or they might be entirely invisible, dark, dense ghosts hidden in the night sky. It's also possible that quark novas produce tiny fragments of strange matter, strangelets that drift through space. If one ever passed through our solar system, it might leave behind a detectable signal. Or it might pass silently, a whisper of the universe's deepest machinery. The challenge is, we can't replicate these conditions in a lab. We've seen quark-gluon plasma in high-energy particle colliders like the LHC, but only for trillionths of a second. To study a quark nova would require instruments sensitive enough to detect and decode the signatures of matter collapsing beyond the known limits of physics, from millions or even billions of light years away. But if we ever catch one in the act, if we see that second explosion, it would be a revelation. It would mean that even after a star dies in fire, even after it's crushed into a neutron core, there's still another layer of truth to uncover. A deeper breakdown, a more violent rebirth, a final scream from the corpse of a star. Where matter breaks, gravity wins, and physics bends. Imagine an entire star collapsed down to the size of a city. Now imagine that star spinning dozens, even hundreds of times every second. Its surface harder than steel, its magnetic field strong enough to shred atoms, and its gravity so intense it could crush a mountain into dust. This is a neutron star, one of the most extreme, bizarre, and fascinating objects in the universe. When a massive star, several times the mass of our Sun, reaches the end of its life, it explodes in a supernova. What's left behind, if it doesn't become a black hole, is a core that's been compressed beyond comprehension. Protons and electrons are crushed together into neutrons, and the whole thing becomes a sphere just 20 kilometers across. That's the size of a city, but it contains more mass than the entire Sun. The result? Gravity so strong that if you stood on the surface, assuming you somehow could, you'd be pulled down with a force billions of times stronger than Earth's gravity. You wouldn't just fall, you'd be torn apart, instantly. But it's not just about gravity. It's about density. A single teaspoon of neutron star material would weigh around 10 million tons, more than every skyscraper in New York City combined. That's not a metaphor. That's real. And the deeper you go beneath the crust, the stranger things get. The outer layer is thought to be a thin, ultra-rigid crust, maybe a few hundred meters thick, where atoms are stretched into long, crystalline chains by the crushing pressure. Beneath that, a sea of degenerate neutrons behaving like a quantum fluid we don't yet fully understand. Deeper still, things may get even weirder. Some scientists believe the core of a neutron star could contain quark matter, where neutrons themselves break down into a sea of free-floating quarks, the fundamental building blocks of matter. Others think hyperons, particles we barely understand, may emerge. Whatever's inside, we know this. It's beyond anything we can recreate on Earth. Even space and time behave differently near a neutron star. Time ticks more slowly the closer you get. Light bends so sharply under the star's gravity that from the right distance, you can see more than half its surface at once. It's like watching a sphere that's been turned inside out. And many neutron stars spin, fast. Some rotate dozens of times per second. A few spin hundreds of times per second, faster than a kitchen blender. These are called pulsars. They emit beams of radio waves or X-rays from their magnetic poles. As the star spins, those beams sweep across space like cosmic lighthouses. Every time the beam points toward Earth, we detect a pulse, regular and precise. So precise, in fact, that some pulsars are used as cosmic clocks, accurate enough to rival atomic timekeepers. But that's not all. Neutron stars can flare up. If a neutron star is in a binary system, it can steal matter from its companion. As that gas spirals inward, it heats up, emitting X-rays. The impact of even a pebble-sized bit of matter hitting the surface would release an explosion of heat and light. Just a single grain of sand could unleash a burst of energy greater than any bomb. And then, there are the monsters among them. Magnetars. These are neutron stars with magnetic fields a quadrillion times stronger than Earth's. Strong enough to distort atoms. Strong enough to trigger starquakes. Fractures in the crust that release bursts of gamma rays powerful enough to be detected across the galaxy. In 2004, one magnetar flare briefly distorted Earth's ionosphere from 50,000 light-years away. Neutron stars sit on the edge of possibility. If they gain just a little too much mass, through a merger or a long, slow feeding process, they can no longer resist gravity. Their quantum forces collapse. The star contracts again. And this time, it doesn't stop. It becomes a black hole. That's the razor-thin line neutron stars walk. They are cosmic tightropes, balancing between extreme pressure and total collapse. They shouldn't exist, but they do. And they tell us, in every pulse, every flare, every strange gravitational signal, the universe has more layers than we've yet begun to understand. When magnetism rewrites the laws of matter and space, there are black holes that bend space. There are neutron stars that crush atoms. And then there are magnetars, objects so strange, so intense, that even the rules of physics start to unravel near them. These are not just neutron stars, they are the most magnetic objects known in the universe. To understand how extreme that is, let's start with Earth. Our planet has a magnetic field. It moves compasses, protects us from solar radiation, and powers auroras. But a magnetar's magnetic field is a quadrillion times stronger than Earth's. That's a 1 followed by 15 zeros. It's so strong, it doesn't just affect metal or particles. It warps atoms, twists quantum fields, and reshapes empty space itself. Near a magnetar, electrons are forced into narrow paths. Light behaves strangely, becoming polarized, scattered, even slowed. Quantum theory predicts that empty space near a magnetar can act like a lens or a prism, bending photons in ways we don't see anywhere else. And most of the time, they're quiet. Magnetars typically rotate slower than regular pulsars, maybe once every few seconds. They emit low levels of X-rays and gamma rays, barely detectable unless you're looking closely. But then, they snap. Over time, the immense magnetic field twists the crust of the neutron star. Just like Earth's crust can shift and crack during earthquakes, a magnetar's crust can suddenly fracture. When that happens, the magnetic energy stored within is released all at once. This is called a giant flare, and it is terrifying. In 2004, one such flare erupted from a magnetar called SGR, 1806-20, located over 50,000 light-years away. In a fraction of a second, it released more energy than our Sun will emit in 100,000 years. The initial gamma-ray flash was so intense, it briefly altered Earth's ionosphere. Satellites designed to detect nuclear weapons went off. Instruments were overwhelmed. And yet, we were safe, because the flare came from halfway across the galaxy. If it had occurred just a few dozen light-years away, it could have fried our atmosphere. Since we began observing the skies, only a handful of giant magnetar flares have been seen. Most activity is subtler, smaller bursts of X-rays or soft gamma rays, often from young magnetars still adjusting to their own volatile magnetism. But even the small ones are powerful. Even the quiet ones change what we thought possible. Magnetars exist on the edge of what physics allows. Their fields challenge our understanding of quantum mechanics, relativity, and the structure of matter itself. No laboratory on Earth can reproduce what a magnetar does naturally. They may also be the source of another great mystery: fast radio bursts, or FRBS, millisecond-long pulses of radio waves coming from deep space, some of which repeat, while others flash just once. In 2020, a magnetar in our own galaxy emitted both a radio burst and X-rays at the same time, linking it to the FRB phenomenon for the first time. We still don't fully understand how they form. Some scientists believe magnetars are born from especially massive stars that spin rapidly during collapse. Others think binary interactions or fallback material after a supernova may create the conditions necessary to supercharge the magnetic field. Whatever the cause, once a magnetar is born, it ticks like a time bomb. Its magnetic field decays over thousands of years. As it weakens, the flares become rarer. Eventually, it settles down into a quieter life as a standard neutron star. Today, we know of only a few dozen magnetar candidates across the Milky Way. They blink on, they vanish. Most of the time, they are ghosts, hidden in plain sight. But once in a while, they remind us they're still out there. And when they speak, the entire galaxy listens. Milliseconds of mystery and unimaginable energy. It started with a glitch, or so scientists thought. In 2007, researchers were combing through archival data from the Parkes radio telescope in Australia when they found something odd. A sharp, clear pulse of radio waves, lasting just a few milliseconds, had appeared out of nowhere. It was fast, loud, and gone in an instant. At first, they assumed it was interference, maybe a satellite or even a microwave. But over time, more of these strange signals appeared, from different places, at different times, and they were all coming from deep space. We now call them fast radio bursts, or FRBs, and they may be one of the most puzzling phenomena in modern astrophysics. What makes them so strange? Each FRB lasts only a fraction of a second, yet in that moment, it can release as much energy as the Sun emits in an entire day. That's billions of times more powerful than the radio signal from a typical pulsar, packed into a blip shorter than a blink. They don't come from nearby. So far, every confirmed FRB has originated outside the Milky Way, meaning they had to travel millions or billions of light-years to reach us. And yet, we can detect them. The problem? They leave behind almost no clues, no visible light, no X-rays, just that quick, brilliant radio flash. For a while, no one knew if they were one-time cosmic accidents or repeating events. Then came a breakthrough. Some FRBs repeat, not regularly, not predictably, but they do come back. That changed everything. If they could repeat, that meant the source wasn't something that self-destructed, like a supernova or a neutron star merger. It had to be something that could survive its own outburst, which led scientists to Magnetars. In 2020, a magnetar inside our own galaxy was caught emitting a fast radio burst and X-rays at the same time. The first direct evidence linking FRBs to known celestial objects. It wasn't as powerful as the ones from distant galaxies, but it was a crucial clue. Still, not all FRBs behave the same. Some repeat, others don't. Some appear isolated. Others come from regions rich in star formation. A few might even originate in dwarf galaxies, places we wouldn't expect such powerful signals to emerge. So what could be causing them? There are theories. Magnetars, cracking their crusts and snapping magnetic field lines. Neutron stars in tight binaries, whose magnetic interactions unleash bursts. Black holes consuming dense stars, releasing energy as matter is torn apart. Even more exotic ideas, like cosmic strings, dark matter annihilation, or yes, even alien technology, have been floated. To be clear, there's no evidence for intelligent origin. But FRBs are so weird, so unpredictable, and so unlike anything we expected, that no idea is entirely off the table, yet. As these signals travel through space, they pass through intergalactic plasma, which disperses the radio waves by frequency. By studying this delay, how the higher frequencies arrive just a bit sooner than the lower ones, scientists can actually map the matter between galaxies. In other words, FRBs aren't just mysteries. They're tools, beacons from the deep, that help us understand what space is made of. And we're getting better at catching them. New arrays like CHIME in Canada and telescopes like FAST in China are designed to watch wide swaths of sky in real time. They've caught hundreds of FRBs, helping us build a catalog of these elusive flashes. Still, most of the time, they come without warning. A pop, a pulse, gone. And from that whisper in the radio sky, we try to pull back the curtain on a universe still filled with secrets. So the next time you look up at the stars, remember, somewhere, a burst of radio energy may already be racing toward us, crossing billions of light years in milliseconds, just waiting to say hello and vanish. Gravity's final triumph and the birth of darkness. There is a point where physics gives up, where matter collapses beyond all resistance, where not even light can escape, where space curves so steeply it folds in on itself. This is the realm of the black hole, and it begins with a collapse. When a massive star, at least 20 to 30 times the mass of the Sun, runs out of nuclear fuel, its core can no longer fight back against gravity. Fusion slows, pressure drops, and gravity wins. The outer layers fall inward at incredible speed. The core compresses, tighter and tighter, until it passes the neutron degeneracy limit, the point beyond which even tightly packed neutrons can't hold back gravity's crush. There is no explosion, no bounce, just collapse. Down and down, past all known states of matter, until the core becomes an infinitely dense point. A singularity, surrounded by an invisible boundary known as the event horizon. That's the birth of a black hole. From the outside, it may look like the star just vanished. But in reality, it's still there, just compressed into a region so warped by gravity that nothing, not even light, can escape its grasp. This is gravity at its purest. Not just pulling on matter, but pulling on space and time themselves. And black holes don't have to start with stars. If enough gas gathers in one spot, it can collapse directly into a black hole without ever forming a star. If two neutron stars merge, they might create a black hole as a final act. And in the early universe, under conditions we can only speculate about, primordial black holes may have formed from quantum fluctuations in the first moments after the Big Bang. These black holes vary in size, from a few kilometers across to millions or even billions of kilometers in diameter. The smallest, called stellar mass black holes, form from stars. The largest supermassive black holes sit in the hearts of galaxies, weighing millions or billions of solar masses. And yet, they all share one defining trait: a boundary beyond which nothing returns. The physics here grows fuzzy. Inside the event horizon, we don't know what happens. Relativity breaks down. Quantum theory falters. Space and time may switch roles. Some models predict a central singularity. Others suggest something more complex, a core of exotic matter, or perhaps a wormhole to another universe. But here's the amazing part. Black holes don't just sit there. They can grow, merge, and even launch jets of energy that blaze across galaxies. When matter falls toward a black hole, it doesn't always fall in cleanly. It spirals into an accretion disk, heating up as it rubs against itself. This disk can glow with X-rays and gamma rays, sometimes becoming the brightest source of light in the sky. In some cases, black holes even launch relativistic jets, beams of plasma moving at near light speed aligned with the black hole's poles. We don't fully understand how they form, but they can stretch for hundreds of thousands of light years, influencing entire galaxies. Ironically, the darkest objects in the universe can also be the most brilliant, but only just outside their boundaries. And then, there are black hole mergers. When two black holes spiral into each other, they generate gravitational waves, ripples in space-time itself. These waves were first detected in 2015 by LIGO, confirming a century-old prediction of Einstein's. The merger released more energy in gravitational waves than 3 suns' worth of mass, in just a fraction of a second. Today, we routinely detect these events. We hear the chirp of colliding black holes across the cosmos, like the universe whispering secrets through the fabric of reality. But the most haunting thing about black holes is what they represent. A limit. A line where physics, as we know it, stops working. They are puzzles wrapped in darkness, not evil, not destructive, just inevitable. Black holes are the final word of gravity, and their formation marks the beginning of a mystery we've only just begun to explore. When black holes go on a feeding frenzy and light up the universe, black holes are known for their silence, for swallowing light, for pulling in matter and never giving it back. But sometimes, before the final gulp, they put on a light show. So spectacular, so luminous, that it can outshine entire galaxies. This is the realm of hyperaccretion, when black holes feed not just steadily, but violently. And when they do, the darkness becomes brilliant. Here's how it works. Matter spirals into a black hole in the form of an accretion disk, a swirling, flattened ring of gas and dust that heats up as it moves inward. The friction and compression inside the disk reach such extreme levels that the material glows white-hot, emitting light across the electromagnetic spectrum from X-rays to visible light. The brighter the disk, the more we can see. And in the most extreme cases, when supermassive black holes feed at astonishing rates, the result is what we call a quasar. Quasars are quasi-stellar radio sources. They look like stars in early images, but they're not stars at all. They're the bright, blazing hearts of distant galaxies, lit by black holes devouring matter faster than we thought possible. At their peak, a single quasar can release more energy than 100,000 galaxies combined. Yet all of that light comes from a region no larger than our solar system. Let that sink in. A point of light visible from billions of light years away, powered by a disk of gas being torn apart and heated to 1,000,000 degrees by gravity alone. Some quasars also shoot out relativistic jets, beams of charged particles moving at nearly the speed of light. If one of those jets happens to point directly at Earth, we call it a blazar, and it becomes one of the most variable and unpredictable sources of radiation in the sky. Quasars aren't just fireworks, they're architects. The radiation and winds from hyperaccreting black holes can sweep out vast regions of gas, suppressing or triggering star formation. In some galaxies, quasars may have shut down star birth entirely, leaving behind old, red, quiet galaxies. In others, they may have sparked bursts of new stars, compressing clouds as their radiation carved through space. These feedback effects mean that supermassive black holes and the galaxies they inhabit are not just neighbors, they're partners in evolution. And here's the wild part. Many of the quasars we see today existed when the universe was just a fraction of its current age. That means their black holes had to grow very quickly, feeding at near or even above the theoretical Eddington limit, the balance point where radiation pressure pushes back against gravity. This has challenged astronomers for decades. How did black holes get so big, so fast? Were they seeded by massive stars? Or did primordial black holes jumpstart the process in the early universe? We're still looking for answers. But thanks to powerful telescopes like JWST, we're now observing quasars from when the universe was less than 1 billion years old. And their light is helping us piece together how the cosmos took shape. Quasars eventually calm down. As the black hole runs out of fuel, the light fades. The galaxy returns to a quieter state. But the footprint of the feeding frenzy remains. In the stars, the dust, the chemical makeup of the galaxy itself. Today, the quasar at the center of our own Milky Way, Sagittarius, a star, is relatively quiet. But it likely had its own active phase long ago. And if enough gas falls into it again, it could flare back to life. Black holes may be invisible. But when they feed, truly feed, they become the brightest lighthouses in the universe. And in doing so, they shape the galaxies, the stars, and maybe even the story of life itself. When two stars become one, and chaos follows. Most stars live their lives in solitude, but not all. Across the galaxy, countless stars are locked in gravitational embrace. Binary systems, where two stars orbit each other in an elegant cosmic dance. Some are peaceful, others are anything but. Because over time, their graceful motion can unravel. Their orbits decay, their edges touch, and eventually, two stars that once simply orbited collide. Stellar mergers aren't quiet. They are fiery, turbulent, and deeply transformative. They can give birth to new stars, reshape existing ones, or trigger explosions so strange we're only just beginning to understand them. It starts slowly. Over millions or even billions of years, two stars lose energy through gravitational waves, tidal interactions, or the transfer of mass. Their dance tightens, closer, closer, until one day, distance becomes contact. When they touch, the outer layers of gas begin to blend, pulled by gravity and deformed by tidal forces. The stars stretch, twist, and finally become one. What happens next depends on who's involved. If the two stars are similar in size and still burning hydrogen, the result is often a blue straggler, a single rejuvenated star that burns hotter and brighter than its neighbors. We see these anomalies in old star clusters, where no young stars should remain. Their presence hints at ancient collisions, hidden in plain sight. But not all mergers are this tidy. If one star is a red giant, or the pair have very different masses, things get messy. The smaller star may be swallowed whole. The cores might orbit inside a common envelope, a shared, bloated atmosphere that causes intense friction and instability. This phase is one of the most chaotic moments in stellar evolution. The system can puff out, eject gas into space, or collapse inward. Sometimes what's left is a tighter binary. Other times, it's a brand new star. And occasionally, something explodes. These eruptions are called luminous red novae. They're not as powerful as supernovae, but they're still bright enough to be seen across the galaxy. In 2008, a red nova flared in the Andromeda Galaxy, shining for weeks before fading away. Observations showed it wasn't a typical supernova. It was a stellar collision caught in the act. Another red nova occurred that same year in our own galaxy, from a system called V1309 Scorpii. Archival data revealed the two stars had once been a contact binary, so close they shared an atmosphere. Then, right before the brightening, they merged. The glow we saw was the moment of final contact. It was a before and after snapshot of cosmic transformation. More massive mergers can be even more dramatic. When giant stars combine, their fusion layers ignite in strange new ways. Chemical signatures shift. Internal pressure spikes. Entire layers may erupt. The new star often burns brighter and dies sooner than either parent would have alone. And sometimes, a merger leaves behind more than just a new star. Sometimes, it awakens something exotic. Some collisions may form magnetars, ultramagnetic neutron stars that can twist space and light. Others may lead to rapidly spinning pulsars or trigger gamma-ray bursts, those brief but intense flashes of energy visible across the cosmos. In dense star clusters, where stars are packed tightly, gravitational nudges make mergers more likely. Many of the most massive stars we see today in those clusters may be the result of past mergers, forged not by birth, but by violence. Even in our galaxy's distant future, a merger looms on the horizon. In about 4 billion years, the Milky Way will collide with the Andromeda Galaxy. Most stars will pass by each other harmlessly. The space between stars is vast. But gravitational disturbances may destabilize some binary systems, causing a fresh wave of stellar mergers. Some stars may collide, others may form new pairs. The result will be a reconfiguration of the sky and a whole new generation of stars born from chaos. Stellar mergers remind us that not all endings are final, and not all beginnings are peaceful. In the crucible of gravity, two stars can become one, burn brighter than ever, and change the fabric of their galaxies forever. The drifters of doom, and the crashes that change everything. In the quiet, frigid darkness between the stars, not everything follows a sun. Scattered across the galaxy are rogue planets, worlds without a home, cast out from their star systems, drifting alone through interstellar space. No sunrise, no orbit, just eternal night, and a silent journey through the void. They're rare, but not impossibly so. Astronomers estimate there could be billions of these lonely worlds, and some may be as large as Jupiter. Others could be more familiar, Earth-sized wanderers with frozen oceans, rocky crusts, and buried heat still lingering from their formation. But it's not their loneliness that makes rogue planets so terrifying. It's what happens when one of them gets too close. Imagine a rogue planet, cold, massive, ancient, wandering through space for billions of years. Then, by sheer chance, it passes near a star system. Its path curves inward, gravity drawing it into a slow-motion spiral toward a catastrophic rendezvous. At first, nothing seems wrong. The stars still shine. The planets orbit, but their motions begin to shift, just slightly. A planet is nudged out of its usual track. A moon veers off course, and then, like a wrecking ball in space, the rogue planet gets closer. If such a world were to collide with a planet like Earth, it wouldn't be just an impact. It would be planet-on-planet violence on a scale beyond imagination. The energy released from a planetary collision would be trillions of times greater than any bomb or supernova we've seen from a distance. At the moment of contact, mountains would vaporize, oceans would boil away, and both crusts would melt into plasma. The atmospheres would explode into space. The molten cores could fuse. From afar, the impact might outshine entire stars for a brief moment. And if Earth were the target, there'd be no warning, no evacuation, no chance. Not just the end of life, but the erasure of continents, ecosystems, memory itself. No fossils, no ruins, no one left to remember it happened. But destruction isn't always the end. Sometimes it's the beginning. When planets collide, what's left behind can coalesce into a new world. Larger, hotter, spinning wildly, wrapped in debris. Over millions of years, this debris might form rings, moons, and eventually cool into something stable. Something habitable. Maybe even beautiful. We think this may have happened here. Earth's moon, according to many scientists, likely formed from just such a planetary crash. Billions of years ago, a Mars-sized world named Theia may have struck the young Earth. The debris thrown into orbit eventually formed the Moon, and that ancient impact may have altered Earth's tilt, spin, and even its seasons, shaping the planet we live on today. Other signs of cosmic trauma can be seen across the solar system. Uranus lies tipped on its side. Mercury has a massive metallic core but little crust, possibly the remnant of a cataclysm that stripped away its outer layers. And there's more. Rogue planets don't even have to crash to cause chaos. Just passing by can disturb the orbits of distant objects, trigger comet storms, or disrupt entire systems. They are wild cards, gravity grenades. One close flyby could send a cascade of asteroids inward, or even fling habitable worlds out into the cold, turning them into rogue planets themselves, a chain reaction of instability. So far, we haven't detected a rogue planet headed toward us. But with billions of them possibly drifting through the galaxy, the odds are never zero. They move in silence, and they don't care if we're watching. They are reminders that even the vastness of space isn't empty. That out there, in the dark somewhere, a forgotten world may already be heading this way. When a star gets too close and is torn apart. In the silent ballet of galaxies, stars follow steady paths. They orbit their centers. They move in predictable rhythms. But sometimes, something strays. A single star, wandering too close to a black hole. Not a collision, not a plunge. Just a mistake in distance. What happens next is one of the most violent deaths a star can endure. This is a tidal disruption event, or TDE, and it begins with gravity. Black holes don't need to swallow something whole to destroy it. Even from a distance, their gravitational pull creates enormous tidal forces, differences in gravity between one side of an object and the other. On Earth, tides move oceans. Near a black hole, they rip stars apart. As the star approaches the black hole, the side facing the black hole feels much stronger gravity than the far side. The result? The star is stretched, pulled, and eventually shredded into long, thin streams of plasma. It's called spaghettification, and it's not science fiction. The remains of the star don't vanish instantly. Some of the stellar material escapes, flung outward in dramatic arcs. But much of it falls back toward the black hole, forming a temporary accretion disk that glows brightly with X-rays, ultraviolet, and visible light. From Earth, it looks like a new light has appeared in the sky, sudden, brilliant, and fading over weeks or months. We've now seen dozens of confirmed TDEs. Some show slow rises and long fades. Others flare quickly and vanish just as fast. The light curves, the energy profiles, the emission lines, they all tell stories of mass, distance, and destruction. TDEs aren't just spectacular, they're also incredibly useful. Most of the time, supermassive black holes at the centers of galaxies are dormant. They don't emit light, they just sit in the dark. But when a TDE occurs, that darkness lights up. Suddenly, we know where the black hole is. We can estimate its mass. We can study how it interacts with matter. We can test the physics of accretion, relativistic jets, and even the warping of space-time itself. In 2019, astronomers observed a TDE called AT2019-QIZ, just 215 million light-years away. It was one of the clearest, most complete TDEs ever caught. A star being torn apart in real time, with multi-wavelength observations across the spectrum. It offered a front-row seat to stellar destruction. And there's more. Some TDEs appear to launch jets of material, narrow beams of matter and radiation, like mini-quasars. These are rare, but when they happen, they produce intense radio waves and high-energy X-rays. It's as if the black hole is not just feeding, but firing back. TDEs also help us understand how galaxies evolve. Each flare adds energy to the core of a galaxy. Each event can heat up surrounding gas, disrupt local star formation, or even reshape the orbits of nearby stars. They may even play a role in regulating the growth of supermassive black holes. Brief moments of feeding, separated by long periods of silence. But perhaps most haunting is this. A TDE is not caused by malice. The star isn't foolish or flawed. It simply passes too close. The black hole doesn't chase. It doesn't deviate. It waits. And when the star crosses the threshold, nature takes its course. It's a cosmic reminder. In space, sometimes the greatest danger comes not from impact, but from proximity. Nature's most extreme particle accelerators. They come silently, one by one, without warning. Invisible bullets from the far reaches of space. Each is smaller than an atom, yet some arrive at Earth with more power than a fastball hurled by a professional athlete. These are ultra-high-energy cosmic rays, the universe's most powerful subatomic projectiles. And they defy everything we thought we knew about energy, matter, and motion. Most cosmic rays are common. They're born in solar flares, supernova remnants, and the occasional stellar outburst. But every once in a while, something different appears. A single particle, accelerated to such extreme energy that it puts even our most advanced machines to shame. Take the Large Hadron Collider, for example. It's the most powerful particle accelerator on Earth, smashing protons together at nearly the speed of light. It can generate collisions with energies up to 13 trillion electron volts. That's enough to probe the deepest layers of matter and unlock the forces that shape the universe. But to an ultra-high energy cosmic ray, the LHC is child's play. Some of these particles carry more than 100 quintillion electron volts. That's millions of times more energy per particle than anything we've ever built. Packed into a particle smaller than a proton, and we have no idea where they come from. They don't travel in clouds. They don't follow predictable paths. Instead, they arrive sporadically, crossing unimaginable cosmic distances. Their paths are warped and tangled by magnetic fields along the way, making it almost impossible to trace them back to their source. Some scientists believe these particles originate from violent places, the accretion disks of supermassive black holes, or jets from gamma-ray bursts, the death throes of massive stars, but these are guesses. We've only observed a handful of these rays. They're so rare that, on average, only one hits each square kilometer of Earth every 100 years. When they do arrive, they never hit the ground directly. Instead, they collide with atoms high in Earth's atmosphere, causing a cascade of secondary particles. Like a microscopic bullet hitting a pane of glass, they shatter atoms and send fragments flying. Particles that rain down across miles of sky. Places like the Pierre Auger Observatory in Argentina have built massive detector arrays to catch the fallout from these rare cosmic strikes. By analyzing the shape and spread of these secondary particle showers, scientists try to reconstruct the original ray, its energy, direction, and possibly its source. It's like trying to figure out what kind of stone made a splash in a pond just by looking at the ripples. Complex, frustrating, and utterly fascinating. But why study them at all? Because ultra-high-energy cosmic rays might be the key to discovering new physics. They could help us probe the quantum structure of space itself. Some physicists suspect that space isn't perfectly smooth, but has a grainy texture at the smallest scales, something we might detect only through the behavior of particles this powerful. They may also offer insights into extra dimensions, dark energy, or other exotic features of the universe that are beyond the reach of terrestrial labs. We like to think of our particle accelerators as symbols of human progress. And they are. But these cosmic rays are a humbling reminder that somewhere out there, nature is already doing what we can barely imagine. Flinging lone particles across billions of light years with energies that crush our understanding of what's possible. They're not just messengers, they are challenges from the universe itself. Cosmic strings, vacuum decay, and the edges of what we dare imagine. Not all power in the universe comes from what we can see. Not all threats are loud. Some lie buried in equations, in probabilities so small we think we're safe, until we remember, the universe doesn't need our permission to surprise us. Welcome to the domain of theoretical extremes, concepts so wild, so far beyond current observation, they live at the edge of physics itself. And yet, they might be real. Cosmic strings. Imagine the early universe, a seething, boiling sea of energy just moments after the Big Bang. As it cooled and expanded, physicists believe it may have undergone phase transitions, like water freezing into ice. But space isn't water. And when it changes states, it might leave behind defects. Cosmic strings are one such defect. Ultra-thin, ultra-dense filaments of energy stretched across the universe. Thinner than a proton, yet possibly as massive as a mountain per centimeter. They would slice through space like blades, warping time around them. If two strings ever intersected, they could release bursts of energy in the form of gravitational waves. Ripples in space-time so sharp and sudden, they might be detectable across billions of light years. We've never seen one. But we're listening. Vacuum decay. This one is unsettling. In quantum field theory, the vacuum, the baseline state of space, isn't guaranteed to be truly stable. We might live in what physicists call a false vacuum, a local minimum of energy, stable for now, but not forever. If, somewhere out there, a bubble of true vacuum spontaneously forms, it would expand at the speed of light, converting everything it touches into a new state of physics. Particles would gain different masses. Forces would change. Chemistry would unravel. Life would end, not with a bang, but with a rewiring of reality itself. And we'd never see it coming, because it would hit us before the light from it arrived. Vacuum decay isn't just a theoretical horror story. Some models of particle physics suggest it's not only possible, it might be inevitable. But maybe not for billions of years. Or maybe it already happened, and it just hasn't reached us yet. Other hypothetical monsters, gravastars and fuzzballs, alternatives to black holes that avoid singularities altogether. They're dense, compact objects with exotic matter at the core, or string theory-based structures with no interior at all. Some might look like black holes, but aren't. And if they exist, they could solve some of the deepest paradoxes in modern physics. Computronium collisions. Imagine matter rearranged not for stability or life, but for computation, the densest, most efficient possible structure for processing information. If such a system collided with another of its kind, the resulting release of computational energy might mimic natural disasters, or give rise to something entirely new. Causality engines. Devices or phenomena that extract energy not from motion or heat, but from the gradient of time itself. The difference in how time flows from one region to another. Still pure speculation, but grounded in questions we haven't yet answered. Is time truly uniform? And if it isn't, can it be mined? All of these ideas share a common thread. They lie beyond what we can confirm. They may be impossible. But physics isn't about certainty. It's about asking questions bold enough that the answers change how we see everything. We've spent this journey exploring supernovae, neutron stars, black holes, kilonovae, and gamma-ray bursts, the known titans of destruction and creation. But sometimes, the most powerful things in the universe are the ones we haven't seen yet. The ones that live in equations, in theories, in whispered possibilities at the edge of math. And the next great discovery might not be a bigger explosion. It might be a quiet shift in the cosmic rules, one that redefines energy, matter, and what it even means to exist. So, what is the most powerful thing in the universe? After all this, after the explosions, the collapses, the jets and the flares, the broken stars and shattered space, you might still be wondering, what's the answer? What's the most powerful thing in the universe? Is it the supernova, that stellar death scream that lights up a galaxy? The gamma-ray burst, a split-second beam that makes the cosmos blink? The black hole, silent and unrelenting, that swallows everything, even time? Or the theoretical vacuum decay, a quiet whisper that could erase all existence? Each is powerful. Each reshapes the universe in its own way. But the real answer might not be an object or an event. It might be a principle, change. Every force we've explored, every burst, flare, or collapse, is a transformation. A star becomes a remnant. A merger becomes a black hole. Matter becomes light. Order becomes chaos. But always, something becomes something else. Power in the universe is not just about destruction. It's about transition. About the ability to reshape reality, whether through fire, gravity, quantum breakdown, or the invisible pull of magnetism. The most powerful thing in the universe is whatever comes next. The force that rewrites the rules, that remakes matter, that surprises us, that reminds us the cosmos is still growing, still changing, still becoming. And we, tiny, fragile observers on a pale blue dot, are just beginning to understand the scale of that power. Thanks for watching. If this blew your mind like it did ours, make sure to like, subscribe, and share the wonder. Because out there, beyond the stars, the universe is still writing its story. And we're lucky enough to read a few pages.